Now see, here with respect to the first binary operation, it is a commutative group, but with respect to the second binary operation, it is just a semi-group. So it just holds an associative law. So what more axioms can have a possibility of addition? An identity element can be added with respect to the second binary operation. An inverse element can be added with the respect to the second binary operation. Commutativity can be added with respect to the second binary operation, if I am not wrong. If with respect to dot there exists an identity element, then that identity element is called unity element. If unity element, and hence the ring will be said to be a ring with unity E prime. Similarly, with respect to dot, if commutative property is satisfied, then such a ring will be called a commutative ring. Now, if both the axioms are present in the ring, then it is a commutative ring with unity. So, not only ring is the structure, with ring further, if unity element is present with respect to the second binary operation, if commutativity is present with respect to the second binary operation, if both the properties are present with respect to the second binary operation, then we have these different structures. Examples. Now, first basic examples start with set of real numbers, set of rationals, set of complex numbers, set of integers with respect to plus dot, where plus and dot are usual addition and usual multiplication. So whatever addition and multiplication definition we already know, so that is called usual addition and usual multiplication. So addition and multiplication here have their usual definition, and we have just taken some sets here which are basic real numbers, complex numbers, rational numbers, integers. Now in each of these, with respect to addition, all of them form a commutative group. Now it's very simple, since with respect to addition it is always associative, that is a plus b plus c equal to a plus b plus c. So this kind of addition is applicable for any element, whether it is an integer, whether it is a complex number, whether it is a rational. For complex number we will just replace it by complex, that is ABC will have forms of a1 plus I a2, b1 plus I b2, c1 plus I c2, and hence like that. So associative. What will be the possible identity element? Additive identity element. Any element added with 0 gives us the element itself, and for complex numbers 0 can also be written as 0 plus 0i. So it has the existence of additive identity. Next, presence of inverse, just the negative of the number. So if I add a with minus a, it gives us 0 from both ends. So minus a is the additive inverse for a, or a is the additive inverse for minus a. So that happens for every possible element of real numbers, and hence for rationals and integers, because they are subset of real numbers, and as well as complex numbers. So existence of additive inverse is there. Commutativity of course prevails. I think it need not be highlighted. So for product also, that is for multiplication also, it is associative. So it is a ring, or all of them are rings. Now with ring further I can add this, that they are commutative rings with unity. All of them are commutative rings with unity, because for every one of them with respect to multiplication it is a commutative group, semi-group with respect to multiplication. So with respect to multiplication, I can always write a dot b equals to b dot a for any, whether it is a real number or whether it is a complex number. So it has identity element. It has commutativity. Next, will it have unity? Unity means multiplicative identity. So with respect to multiplication, does it have identity element? Yes, it does have identity element. What is the identity element? Any element multiplied with 1 gives us the same element back. So that is the unity element. So all of them are commutative rings with unity. In case of existence of multiplicative inverse, I have not still defined existence of multiplicative inverse. So let us just check. Any element, real number, has inverse as its reciprocal element. It may be same for rationals or complex number, but for integers, if 2 is an integer, can it have a inverse half? I think not. So therefore, because half is not an integer, so therefore for this particular ring, it does not have a multiplicative inverse for non-zero elements. But still, for all these rings or commutative rings with unity, they do not have multiplicative inverse because 0 element is present in all these rings and 0 does not have inverse. So therefore, they are all rings, commutative rings with unity, but the axiom that cannot be interpreted with the second binary operation multiplication is the existence of inverse. Next, I come to more examples. The second set of example is nz plus dot. What is n? N is any natural number. It belongs to set of natural numbers. Nz. So nz means natural number. So it is just the subsets of z. Say twice z, thrice z, fourth z, 5z, 6z. So multiples of 6. In integers which are multiples of 6. Integers which are multiples of 3, and so on. So there here integers which are multiples of the natural number n. So of course it is a commutative ring with unity because it is a subset of z. So that is an example. Next, third example will be set of all matrices. I have given you the class notes. I have already shared you the class notes. Just look into that when you are studying this material parallelly. So you will see what is M and R. M and R is the set of all matrices of order n with real entries. So what is it? Set of all matrices of order n with real entries. So with respect to addition, it will form a commutative group where additive identity is the null matrix, all entries 0. Additive identity is the null matrix, all entries 0, and the unity element shall be identity matrix. Unity element is the identity matrix. And of course existence of inverse is there. If A is a matrix, then negative of that matrix, if you add, then it will generate the null matrix from both sides. So negative of a matrix is the additive inverse of any matrix. And of course matrix addition is commutative, so it will be with respect to matrix addition. So now here plus and dot, I forgot to just tell you that here plus and dot are not usual addition, usual multiplication. It is not effective here. So here the binary operation defined shall be matrix addition and matrix multiplication. So under addition it is a commutative group, under commutative also B plus A. Of course matrix is addition is associative. Now with respect to dot, it has existence of associativity. So it will form a ring. Moreover, since it has presence of unity, this will form a ring with unity. But matrix addition is not always, matrix multiplication is not always commutative. I cannot say A into B is equal to B into A always. So therefore I cannot say it is a commutative ring with unity, it is just a ring with unity. Next I come to the fourth example, which is Zn. Now with Zn I have talked so much in class. I think you all have understood by now that what is Zn. Zn is the set of all classes, residue classes modulo n. Set of all residue classes modulo n. What does that mean? Residue classes means remainder classes. So what is it? Will compose of all these sets which are actually the remainder classes. What is meant by a remainder class? It is an equivalence class. They are equivalence classes, and each remainder class will contain those integers which when divided by n will generate that element as the remainder. So of course remainders are non-zero, and remainders are all zero or positive. They cannot be negative. So therefore all the positive remainders in Zn are 0, 1, 2 up to n minus 1, and all of them are represented as classes. Now what is the zero class? All the integers divisible by 0. Class 1, all the integers when divided by n generates remainder 1. Similarly remainder 2, remainder n minus 1. If remainder n, it will again belong to the 0th class. If remainder n plus 1, it will again belong to the 1th class, and so on. So this is Zn. Now over Zn, if we have two classes, A plus B is denoted as A plus B whole class. A class dot B is denoted by A dot B whole class. These are the binary operations defined on A. Now of course they are binary operations because it will be closed under those operations. That you please verify whether they are binary operations or not. You please verify whether they are rings or not, and of course they will be commutative rings with unity element. So please do verify Zn. I have I think talked about Zn a lot in class, so everybody should have some idea, and please just do it. So there are several more examples. I have shared the problems in email. You will see, go through it. You will see that in the first problem I have told about set of all polynomials. So our example, set of all polynomials over R. So that I will be calling as Rx. So what is Rx? It is the set of all polynomials over R. So of any degree, set of all polynomials of any degree, where if plus g whole x is defined as fx plus gx, and f dot gx is defined as fx into gx, that is product of two polynomials and addition of two polynomials. These will be binary operations, since product of two polynomials is again a polynomial, and addition of two polynomials is again a polynomial over R only. So they are binary operations under which they will form commutative rings with unity, where 0 polynomial will be the additive identity, 0x, 0 polynomial, and inverse of any polynomial will be the negative of the polynomial, additive inverse of course, and commutative of course polynomial multiplication is commutative, so it will be a commutative ring. And with respect to product 1, constant 1, it is also a polynomial, so it is the unity element, so it is a commutative ring with unity.